Dubai, and welcome. Thank you very much, everyone, for joining in today. My name is Tanmay Bakshi. I'm from Toronto, Canada, and just before I begin, I'd like to say a huge thank you to the entire team at SME Beyond Borders for putting together this amazing event. And of course, Nadeem Hood, Rushika Bhatia, and of course, Gina Larson for actually inviting me to this fantastic event and making this all possible. In fact, this is actually, as Rushika mentioned, my very first time in Dubai, and I'm already really loving it here. And I do look forward to visiting Dubai many more times in the future. To start today, I'd like to tell you all a little bit about my background and what I like to do. I am an AI developer and neural network architect, as well as an algorithmist at Darwin Ecosystem. I'm also an author, TEDx and keynote speaker. I'm a YouTuber, course instructor for Udemy, IBM champion for cloud, honorary IBM cloud advisor, and the host of an IBM Facebook Live series called Watson Made Simple with Tanmay. Thank you. Thank you. So as you can tell, I am really passionate about the powerful backend that goes behind services like IBM's Watson, which is, without a doubt, services like artificial intelligence and big data, which, as we speak, is impacting thousands of fields across the globe. However, I would like to say one thing here, and that is that I'm only here because I'm passionate about these technologies. I love to work with artificial intelligence and big data. I'm by no means a subject matter expert on this topic. Instead, I really look forward to actually learning from the true SMEs on these topics, the rest of the speakers and attendees of this conference. But I also know one more thing, that while I can't make predictions, because of course I'm not a subject matter expert, there's one thing for sure, and that is that within the next 4 years, AI will become a central part of any field, any industry, or any company in general that is impacted by technology. However, when working with really powerful technologies like AI and big data, there are always fears that surround it. Some fears including that it's going to overpower us, or it's going to be replacing us at our jobs and what we do. And well, I'm here to tell you that that is simply not true. In fact, the CTO and VP of IBM Watson himself, and my mentor, Rob High, agrees. He says that cognitive computing, which is often called AI, is not a replication of the human mind in the first place. It's a set of intelligence capabilities that provide strength and leverage to our human mind, that fills in gaps where we have limitations. And so, in the next few minutes, I'd like to prove this to all of you. And I'd also like to touch upon one more thing, and that is, why machine learning? Why do I choose to use neural network technologies and machine learning technologies over our regular, naive, tried and tested methods that we know work, like naive AI methods? And well, it's for a simple reason. And that is that our naive AI techniques eventually get saturated. Say we're using a support vector machine, and we need to understand huge amounts of data. Over time, when you feed in really, really big amounts of data, it just saturates itself. It won't get more accurate. If anything, it'll just go down. And so, that's why I love new machine learning techniques, because they allow us to leverage the big data of which we now have an abundance. And so, what I've done is I've handpicked 3 of my projects that I've worked on that I think you'd find most interesting. They're in the fields of security, utility, and healthcare. And I'd now like to start off in the field of security with a new project of mine called Face ML Vault, which stands for Face Machine Learning Vault. As you know from the name of this project, it uses deep learning algorithms for facial recognition tasks. But a question I get a lot is, well, How? Didn't I just show you that neural networks are data dependent? Without big data, they don't work nicely. So a user won't go around taking hundreds of pictures of themselves just to train a neural network technique. So how will I do this? Well, it's through a technique that I like to call facial semantic vectors, or FSVs for short. Now, before you can understand facial semantic vectors, though, you have to understand natural language semantic vectors first. So take a look at this diagram and say that you're building a chatbot. This chatbot will either give you the current weather or it'll reserve a table at a restaurant for you. Now, of course, neural networks don't understand natural language in its current form in words because it can only understand numbers. So, what I do is I convert these words into a list of word vectors, which actually encapsulate the semantic representation of every single individual word within a mere vector. That's right, these things are really powerful, and they represent the semantics of every single word. But then again, the very same words, or very same word vectors, put in a different order, could mean an entirely different thing. So, what I do is I then use a neural network on those word vectors, and I create a sentence semantics vector, which represents the actual semantic representation of the entire sentence in a vector, which is then classified into the final output. Are you asking for the weather, or are you asking to book a table at a restaurant? But in order for you to figure out how powerful these vectors truly are, let's take a look at an example. Now let's just say you found the word vectors for the word king. Okay, simple enough. Now you negate the word vectors for the word man. Then you add in the word vectors for the word woman. As a human, you know the result. You know that the result is queen. Because it's simple. You're taking king, you're negating the man representation, you're adding the woman representation, and you should get queen. But what's really fascinating is even computers get this correct. In fact, taking a look at this chart, you can see that there's woman on the chart, there's man, there's king, there's queen. In your mind right now, you can actually go ahead and sort of visualize what it would look like if you were to take those individual dots on that word vector graph, and if you were to actually negate man from king and add in woman, you can see that it lands very, very close to queen. And that similarity, that closeness, is what tells the computer that this is the word. But anyway, let's get back to facial recognition. Now, how do we apply this to facial recognition? Well, what if I trained a neural network on facial recognition data? Then what I do is I feed in a new face. The neural network is then able to create a vector that describes the semantics of my face. It perfectly describes what my face looks like, and only in the details that matter to facial recognition. If I were wearing, say, blue glasses right now, which I am, then it would not count that in the image. It would only count the fact that my face looks like, and then a vector. It would not count those insignificant details that don't count towards what I look like. So that is a facial semantic vector. In fact, let's visualize it. Let's say I took two images of Steve Jobs, two entirely different images. One is black and white, one is color, one is low res, one is high res, one has a better shot of his eyes, one has a better shot of his ears. There are literally uncountable differences between these two images. Yet, when you look at the right of the image, look at those two graphs, look at how similar those two graphs are. Those are the facial semantic vectors for Steve Jobs. Both of those faces calculated independently. Look at how similar they are. Similarly, for two of my faces, even though the skin tones at this point are practically entirely different, it still gives me such a similar facial semantic vector. But what's really fun is when you look at one image of me and one image of Steve Jobs. Now take a look at how dissimilar the two facial semantic vectors are. And that's the dissimilarity that the neural network picks up on in order to tell me that these are different people. But of course, though, we do not want the facial semantic vectors to count in noise from the background of the image. So how do I solve that? I use IBM Watson's visual recognition service in order to filter out the person's face from the image before running it through the FSV calculator. And then I use Google's Keras library and Microsoft's ResNet, or residual neural network architecture, in order to actually calculate those FSVs. However, when we're working with naive frontal camera facial recognition, there are always a few issues. But there are also some advantages, including the fact that it's really performant, it's really fast, and it is really, really accurate. Because we're just doing a simple 2D image classification. There's no 3D depth map or infrared or anything involved. And that enables a great user experience. Until they find out that their data is not private, and the fact that the system is foolable by pictures and masks, and that it's not compatible with mobile devices. So, through FaceML Vault, I've been able to work around all of these challenges. And I'd now like to show you a demo of FaceML Vault in action. Let's get to it. All right, so as you can see, I'm going to switch over to my computer here, and this is a terminal window. It has all of the FaceML Vault application within it. Now, what I can do is I can actually run the FaceML Vault program. And this will allow me to, of course, actually start recognizing my face. I'm going to look at the camera and smile. But what it's doing right now is it's actually taking its memory of what it knows my face looks like, and it's decrypting it. I'm going to look at the camera, smile for a bit. There we go. It's done looking at my face with that yellow marker, and it's now verifying me. In theory, what it's going to do is it's going to take the older facial semantic vectors, the new FSV that it just calculated, and as you can see, it tells me that I am verified into the system because my current facial semantic vector is very, very close to the facial semantic vector that it knows I am. Now, in fact, one more thing that I'd really like to point out here is, as Yasser mentioned, the airports of the future, automatically checking you in, recognizing your face. This is the type of technology that enables it. We don't need complex hardware, expensive hardware. It's just simple 2D liveness detection in order to make sure that it's not spoofable. But what I think would be really, really interesting is if we show an example of this not working, of it not verifying someone to the system. But the thing is, I can't do that because, well, it's my training data. It's been trained on my faces. So, what I'd like to do now is actually call up a volunteer from the audience and actually see and make sure that the facial recognition system isn't unlocked by your face. So if anyone would like to volunteer, please, oh, great, thank you for volunteering. Great, so just come up on stage, please. All right, so what's your name? George. All right, great. Thank you for volunteering. So now, please stand in front of the Mac, the computer. Let's actually run FaceML Vault. Now, what's going to happen right now, George, is the system is now actually decrypting what it knows my face looks like. And after that, the yellow marker will tell you that it's actually looking at your face. There we go. It's done looking at your face, George. But now what's going to happen is it's verifying. It's comparing your current facial semantic vector to my facial semantic vectors that it has stored. And in theory, as you can see, it tells you that you are not verified into the system. Thank you very much, George. Do you have any questions about how that worked? No? Okay. Okay. Do you have any questions about how the system works? Excuse me? Yeah? Yes, exactly. So what's happening is your facial semantic vector hasn't been preloaded into the system. If I were to train it with your pictures, say 10 of them, then it would have unlocked. But that was a demo of FaceML Vault in action. As you can see, via liveness detection, via all of this technology, it's able to tell me that, in fact, I am allowed into the system, but George here wasn't allowed into my vault. So that was a demo of FaceML Vault in action, how AI, a simple example actually, one example of how AI can be applied in the field of security. But now, I'd like to switch over to the field of utility. Utility is a very broad field, which is why I believe AI can impact a ton of different individual subfields within utility. And so now, I'd like to talk about a brand new project of mine called T-Enhance, which hallucinates realistic details into low-resolution images. That's right, we can take low-resolution images and quite literally enhance their resolution. Let's take a look at an example. Let's just say that I'm a Mac user, and I take a minuscule screenshot of the tiny Apple logo that's on the top left of my screen. Now this is a 21 by 21 image. Let's say I scale it up by 16 times. Now this is a 336 by 336 image. Okay, now if you look on the left, that's a really blurry apple. I would never use that in one of my presentations, ironically. But if you look at the right, that is an Apple logo, enhanced and scaled up 16 times via my neural network algorithm. But what's really, really interesting is this. Well, this is just a simple image of a plane, but you're sitting far away and that plane is really small. So you don't see any JPEG artifacts and you don't see any blurriness. But if I take this plane and scale it up so that you can actually see it, it looks like this, which again, I would never use this in one of my presentations. This is a really low resolution. You can see all the individual JPEG artifacts too. It's really bad. But if I were to scale that up to that size via my neural network algorithm, look at the difference. This is the blurry airplane. This is the smooth airplane. Look at the huge difference. That is called image super resolution through convolutional neural networks. Thank you. Thank you. As I mentioned, it's powered by deep learning algorithms, more specifically convolutional neural networks, on a custom architecture and custom data set that I developed. But an even more interesting demo, I believe, is this. Take a look at this eye here. Okay. Now, if you take a look at all the individual eyelashes, even the reflection in the eye, look at how blocky everything is. That was a really small image of an eye that I just scaled up 3.2 times. Okay, so as you can see, really blurry. But watch this. Through image super resolution, I'm able to convert this to this. All the blockiness is gone. It took the details that it knew, and it expanded the details. It expanded what it knew. It used deep learning to hallucinate what it thought should be in those pixels. It's putting information where information was never there in the first place. But what's really fascinating is when you look at them side by side. So take a look at this. On the left here, you can see the naive upscaling method. And on the right, you can see the smart upscaling method. Take a look at the huge difference between all the blockiness. Even take a look at the reflection in the eyes. All the blockiness versus the final end result via image super resolution through convolutional neural networks. But you may be wondering, why? Why did I implement an image enhancement system for utility? And well, it's because of a simple reason. I'm demoing data enhancement through image enhancement. The point is not that neural networks can make images more high res. The point is that neural networks can create and enhance data where information isn't there. For example, OCR. Now, if you're familiar with optical character recognition, what this basically means is, for example, when you go to a bank and you give them a check, they're not manually typing in all of those check details. They just feed it into a scanner. The scanner uses machine learning, detects everything that's on the check, and automatically reads it. Same thing with the US Postal Service and lots of other places. They automatically detect what you've written on the letter, the address. So let's just say I have a paper like this. Not going to work. OCR is going to have a really difficult time, if at all it will work, with this piece of paper. Because look at all the crumpling, look at how blurry it is. There's practically nothing that OCR can do with this. However, through this very algorithm, you can train the neural network to not only hallucinate in pixels where pixels aren't there, but also remove all those individual fold marks that are there, unnecessarily present in this image. And plus, this exact same algorithm has an application in the field of healthcare. Let's just say that, of course, right now, let's just say I played music in my presentation. Just by chance, I played music, or you're talking on your phone, or someone's eating something beside you. You can do something called audio attention. You can direct your focus to me, and your really smart human brain will only focus on my audio while basically filtering out whatever else is bothering you. Until you, of course, pay attention to it and realize it's there. However, if you have hearing aids, this is very, very difficult, if not impossible, to do. You're hearing everything around you equally through a microphone. And so, through this very algorithm, not only can you enhance and attend on images, you can attend on audio. And what's even more interesting is, of course, audio enhancement. Now, of course, going back to the example of the airplane. When the airplane was far away, pretend it's audio. The audio is far away. The noise is minuscule, but so is the signal. But you can mainly see the signal. However, if someone who has hearing aids wants to hear audio louder, they crank up the audio. But what that does is it magnifies the signal, but also really magnifies any noise that's in the audio. However, if you were to enhance and upscale audio through this algorithm, you won't get any of that noise. If anything, you'll only get a higher quality of the audio out through the neural network system. And in fact, speaking of healthcare, there is another project of mine that is really close to my heart and that I'd like to share with everyone today. And that is the project called The Cognitive Story. Through the cognitive story, we're trying to augment people's lives, and to do so through the power of cognitive computing and AI. In fact, this project is a collaboration effort between Darwin Ecosystem, IBM, Not Rocket Science, and me. The first chapter in this project is all about assisting those with special needs to allow them to live better, easier, and fuller lives. And in fact, I'd now like to play a quick video clip describing the story of Boo, the first person we're trying to help through the cognitive story, and in fact, the origin of the cognitive story itself.
The trip to meet Boo started with a simple tweet from the friend of a mother wondering if artificial intelligence could be used to help a severely disabled 29-year-old woman communicate with her family. Soon, IBM's Tim Duncan reached out to Darwin Ecosystem's Thierry Hubert to explore the possibilities. Within weeks, the two companies organized a research trip into the rural community just north of Toronto, where Boo lives a solitary life, having almost no contact with the outside world. The pair was joined by 13-year-old Tanmay Bakshi, who was recruited to join the team because of his skills with neural network systems. The road to Boo's hometown was sometimes desolate, sometimes blustery, but by the time the team reached the small town, the sun was bright and the sky was blue. It's not home to many, a hamlet like many others, but in this borough, the developers were coming to see just one resident. They arrived at Boo's ready to learn and understand a woman who can only communicate the broadest of concepts and only to those most intimate with her condition. Her name, Boo, comes from a sound she could make as a baby but can no longer make. Boo is quadriplegic, suffering from Rett syndrome, a rare and debilitating neurological disorder. But her parents know when she's happy, when she's irritated, or when she wants to watch TV, the simplest of desires interpreted by the most intimate knowledge. Now the hope is that artificial intelligence can match EEG signals from Boo's brain to what her parents say she's thinking, and a unique language born from cognitive computing can act as Boo's translator to others and relieve her isolation.
So now that you know about the story behind the cognitive story, I'd now like to take you deeper into the technology to show you what we're actually doing. Of course, though, it starts off with the data that we're able to gather from Boo in order to decipher and translate that into what she's trying to communicate, her intent. And in this case, we've decided to use EEG, or electroencephalogram brainwaves, gathered via a custom 3D printed headset for Boo. Of course, though, from there, it's my role in the cognitive story to use deep learning algorithms and neural networks in order to understand those EEG brainwaves and translate them into human understandable natural language. However, a question that I get a lot is, well, how will I train a deep learning algorithm on unlabeled data that we don't understand? And well, it's quite simple. This is labeled data. We can understand Boo because Boo's mom can understand the very broad concepts that Boo tries to convey. And with her help, we're going to be live labeling the training data as it's gathered from the headset in order to train these custom LSTM neural network architectures that I've developed. And due to this, we've given her the title of Intimate Interpreter. You can find out more about the cognitive story at thecognitivstory.com. And that sums up what I had to say about the cognitive story and how we're using the power of cognitive to live better lives. In fact, I believe that AI's use is not just limited to allowing the disabled to communicate. There is so much more that AI is doing within the field of healthcare. In fact, I'm also currently working on another project that's actually meant to prevent youth or teen suicide through the mental health, diagnosing and detecting depression in the youth very, very early. And you'll be hearing much more about that this December. And so I really do hope that in the past few minutes, I've been able to convince you as to why I believe that AI algorithms are not replacing us, humans, at what we do every single day. Instead, AI was created by humans in order to augment human life, augment our skills, amplify what we can do every single day, and of course, save human lives. Thank you very much, everyone, for joining in today. That's what I had for my keynote. Thank you. Thank you.